Hello everyone, welcome to the new lesson of numerical methods. In the last lesson we learned about the Runge method. The Runge method was the general solution technique of ordinary differential equations, and that Runge method actually covers a lot of other special methods like Euler's method or Hans method or midpoint method, also the Ralston's method. So now in this lesson we are going to learn about another extension of Runge method, which is the adaptive Runge method. Okay, so let's dive into the details. So if you just carefully notice the curve here, and it's a special curve of this is the differential equation curve. Okay, in this curve, look at this, at the vicinity of x equal to 2, the curve is changing rapidly. So if you just use the normal Runge fixed step size methods, then there will be some problems. What problems will look like? Look at this. At the point of x2, if you just use small step sizes, in that case you can of course you can actually cover the area of these point. That means at the vicinity of x equal to 2, you can cover this area by using small step sizes of the Runge method, but it will actually increase the overall computational cost in very high. As a result, you cannot just use smaller step sizes arbitrarily. On the other hand, if you just use large step sizes, you cannot just find out the features around the point x equal to 2. As a result, you will not get the proper y variables from this differential curve. As a result, you have to make some trade-offs. But in such cases, look at this, it's a very abrupt change. Okay, for such kind of abrupt changing, we cannot just use the fixed step size Runge method. That will be very much problematic, because beyond this abrupt change, look at these areas. These are very slowly changing areas. As a result, you cannot just use fixed step size Runge method. We need some special techniques for such kind of problems, and that's why we are going to use the adaptive Runge method. So one technique is that we continuously change the step size. It is also known as the step halving method. Okay, how this works? Remember that before solving a problem, that means an ordinary differential equation, we are just given the step sizes. Okay, h, that is the h term. So what we can do, we can either use the fixed step size, or we can just use a different version of the step size. We can just use two different step sizes of which are actually originally the half of the original step size. That means, let's say y1, it designates the single step prediction. That means the original step size that we are given. Using that step size, we are calculating the y1, which is the original approximated result. Another approximated result y2 can be predicted by using two different half steps. Half steps means if we are given the original step size h, we are going to use h by 2 in 2 steps. As a result, we will get a final result y2, which will be much different from the value of y1. The difference between these two values is denoted as the delta term. Okay, delta is denoted as y2 minus y1. Based on these difference, we can actually modify our original result y2 by this formula. Y2 is delta divided by 15, but this formula is empirically achieved for the fourth order Runge version. So this is only applicable for the fourth order Runge version. This is not for other orders of Runge version. So we are just going to show you an example how the step halving method actually works. Okay, let's say we have this function, ordinary differential equation, and we need to solve it through adaptive fourth order Runge method, and we are given the range of the data points from x equal to 0 to x equal to 2, and we have the initial step size, which is h equal to 2. Okay, this is the initial step size, and we are given the initial conditions as well and the true solutions. Okay, so once how we are going to approach the solution. So using the original step size h equal to 2, we are going to find out the value of y equal to 2 with just single step. With a single step we are just calculating the function value, which turns out to be 15.10584. now let's have the step size. Let's say we are just having the step size. The original step size was 2. If we just take the half of the step size, that means 1. So we will get the value of y of 1. That means h is equal to 1 here. We will get 6.20104, and then based on these value I am going to calculate the final result, that means y of 2. Look at this. In here, when we are calculating the y of 1, we are using the previous y result, that means y of 0, which is 2. Okay, now we are just going to use the value of y of 1, which is 6.20104, inside the value of y of 2. Okay, so this 6.20104 it is used here in y of 2. Okay, so in this way we are just having the step size into 2 parts and then calculating the result, the final result, into 2 steps. Okay, so look at this. There is a difference between the two results. Here in a single step we have 15.10584, but here in the double step we have 14.8086249. So there are some differences. So if you just use the special corrected formula for the fourth order Runge-Kutta version, you will see that the approximated error turns out to be minus 0.01622. So this 14.86249, it was the result achieved from 2 step, that means the double step method, and this 15.10584, this was achieved from the single step method. And in the denominator we have 15. This 15 is for the special case of fourth order Runge-Kutta method. We have already seen a couple of slides before. Okay, so once we know the value of approximated error, we are just going to add it to the value of y2, that means the value which are achieved using double steps. Okay, so we just add the value of ea or epsilon a with the value of the double step method, and then we get the final result, which is 14.84627. so because of this double step method or step halving method, our result is much more accurate than the simple fixed step method. As a result, for the cases of abrupt changes, this step halving method will actually work better than the single step method. Okay, but actually you will also have to remember that such step halving method will also increase the computational overhead. You will have much more calculations to cover to get to the final result. Okay, so now let's see that some of the spatial techniques. Remember, this step halving method is also known as Cash-Karp Runge-Kutta method. It's a special name, and this was developed by Cash and Karp. And another special adaptive Runge-Kutta method is also known as Runge-Kutta-Fehlberg method. Okay, in the last lesson we have seen the fourth and fifth order Runge-Kutta methods, the general fourth and fifth order Runge-Kutta method. Those are just some special cases. But in this lesson I am just showing you an adaptive version of the fourth and the fifth order Runge-Kutta method. So these are known as Runge-Kutta-Fehlberg method. So this one is the fourth order adaptive Runge-Kutta method, and this one is the fifth order adaptive Runge-Kutta method. So these are also known as the Runge-Kutta-Fehlberg method. So you have to know the difference. These are the adaptive ones, and in the last lessons we have shown you the spatial original ones. Okay, those were the special cases of original fourth and fifth order cases, and these are the adaptive ones. So you have to know the difference between these two terms. And in these two equations we have the terms k1, k2, k3, k4, k5, k6, and these terms can be denoted with these formulas. So I am not showing you the detailed proof of these equations, that is out of our scope. So if you want to know the details of these equations k1 to k6, you have to go through the literature of the original paper of Runge-Kutta-Fehlberg method. Okay, so in the Runge-Kutta-Fehlberg method we are just going to use this spatial method for controlling the step size. Okay, how we are going to control the step size, because since this one is an adaptive approach, that means we have to change the value of h continuously. Okay, that value of h can be changed by this formula, h new and equal to h present, and multiplied by the proportionate of the delta new by delta present to the power alpha. So there is lots of terms here in these equations. So what are these terms actually? Here h present represent the present step size, and h new represent the newly step size that is going to be used in the next iteration, okay, for the next data point actually. And delta present, it denotes the present computed error, that means the difference between the present y and the previous y, that means the value of the functions actually. And delta new is the desired error limit, that means the error limit that I want to calculate for the next data point. And the alpha is the constant power. So alpha is changed if delta new is greater than delta present. That means if I am increasing the step size, then alpha is going to be used as 0.2. But if I am decreasing the step size, that means delta new is less than delta present. In that case, alpha is going to be 0.25. Okay, these delta new term, this can be calculated with this formula, epsilon and y scale. This y scale can be calculated from the value of these equation. Okay, so epsilon here is an overall tolerance level. So that's how the Runge-Kutta-Fehlberg method actually changes the value of h adaptively. Look at this, the value of h actually depends on the value of the derivative of the function actually. That means as the derivative changes abruptly, this h new is also going to be changed accordingly. If this abrupt change dy by dx is so much abrupt, in that case h new will also decrease, because if dy by dx is reduced is actually increasing very rapidly, it will cause the alpha term to be 0.25. that means delta new is less than delta present. As a result, h new will also decrease, that means the step size will decrease. So that's how the technique works. Whenever there is an abrupt change, h new is decreased, and whenever is no abrupt change, that means that dy by dx, that means the value of the slope is changing very slowly, in that case h new is increased. Okay, so that's how the Runge-Kutta-Fehlberg method works through the step size control method. So to get the details of this step size controlling, you have to go through the literature of the original Runge-Kutta-Fehlberg method. Okay, so let's look at an example. We have given the original differential equation, ordinary differential equation, which looks something like this, and we have to use the adaptive Runge-Kutta method to find out the solution. Okay, we are given the range of the data points and the initial conditions. So I'm not showing you the detailed calculation of this Runge-Kutta method. I have already given you the fourth and fifth order Runge-Fehlberg method. You can use either one of those to get the result. So I am just showing you the result. Okay, so let's say this is the ordinary differential function given. Okay, this is the slope of the curve of the slope of the function. Okay, so look at this, at the vicinity of x equal to 2, we have an abrupt change. So if you use Runge-Kutta-Fehlberg method of fourth order or fifth order, you will see that based on the step size controlling method, we will have much more data points here around the vicinity of x equal to 2. Okay, so that means at the vicinity of x equal to 2, since the value of the slope is changing very rapidly, the step size will actually decrease. As a result, we will have more data points around these abrupt changes. Okay, and where the change is very slow, that means here in these regions, look at this, the change is very slow. As a result, there are much less data points. That means the step size is actually increased in these areas because there is no abrupt changes. Okay, so based on the abrupt changing of the slope of the function, there are actually changing in the step size. Okay, so that's how the Runge-Kutta-Fehlberg method works for abrupt changing. Okay, So there are some advanced multi-step methods for solving ordinary differential equations. Till now we have seen that we are actually using a single data point to estimate the data point, next data point. So like the Hans method, midpoint method, or the Euler's method, or the Runge method. So for all of those cases, we have seen that based on the single data point, we are predicting the next data point. So this is a single step method. But we can also use multi-step method. That means based on the previous sum results, that means we are using 3 data points here to approximate the next fourth one data point. So this is a multi-step method. So multi-step methods are very much complex, so I am just showing you some of the methods that you can follow for more better results, for more accurate results. And some of those methods like non-self-starting Hans method, also the modified Newton-Cotes formula, Adams-Bashforth open formula, Adams-Moulton closed formulas, then also the Milnes method, fourth order Adams method. These are the special methods for multi-step methods, multi-step ordinary differential equation solving techniques. So you can go through the details of those special techniques. These are very much advanced, and those can be used, those can be helpful for you for your research or project. Okay, so in this lesson we have learned about the Runge-Kutta-Fehlberg method, the step and the step halving method. These are the two special methods that I have discussed under the adaptive Runge-Kutta method. Okay, so both of these methods are actually adaptive, and I have also illustrated graphically what adaptation means, actually how the change of the how the step size changes based on the value of the slope. Okay, so I have also solved an ODE for step size halving method and Runge-Kutta method. So you can go through the detailed calculation using the Runge-Kutta-Fehlberg method formulas. Although I have not shown you the detailed calculations, so it's your homework to calculate the to go through the detailed calculation. Okay, so please go through the detailed MATLAB code that I have attached for step halving method and Runge-Fehlberg method. Those are very straightforward implementation in MATLAB code, so please go through the details of the code. So in the next lesson I am going to cover the last lesson under this section, which is the boundary value problems. So till then, thank you so much.